Hello everyone, I'm J Wildberger, and today we're going to be talking about matrix arithmetic fundamentals. So this is a very classical subject, but there is in fact a more modern take on the whole story, which is something called Maxwell theory, which I've put out in the last few years. You can check that out on the Math Foundations series of videos, Math Foundations 166 to about 173. All of those videos are on Maxwell's and Vexels, which give a sort of a bigger picture in which matrix theory sort of has a more consistent and general arithmetic. Okay, but we're not going to mention that anymore. I'm just going to show you the classical stuff, but just to let you know, there is a higher level. Okay, so with matrices, we look at arrays of numbers. Okay, so the first operations are just addition and subtraction of matrices. And the crucial thing there is that the matrices have to be the same size. So only for matrices of the same size. Okay, so we've already had a look at this in some special cases, but for example, let's say you have 1, 2, 3, 4, 5, 6. There's a matrix, and another one may be 2, 1, 4, 7 minus 3, 5. Okay, to add those, you just add them component wise. So you get 3, 3, 7, 11, 2, and 11. Okay, and to subtract them, well, again, you just do everything component wise. You would get 1 minus 2 is minus 1, 2 minus 1 is 1, 3 minus 4 is minus 1, 4 minus 7 is minus 3, 5 minus 3 is 8, and 6 minus 5 is 1. Okay, so they're just, these are component-wise operations. Okay, so the operation of addition and operation of subtraction. There's another operation of just multiplying by a scalar. So scalar multiplication. So for example, if we take 3 times the matrix 1, 2, 3, 4, 5, 6, then we get the matrix 3, 6, 9, 12, 15, and 18. Okay, so we just multiply all the components. So that's we have these 3 operations which are all component-wise. Now, one way of describing that efficiently is in terms of some notation. So if A is an M by N matrix, so that, I remind you, that means that it has M rows and N columns, then it will have the form like this. We've seen this kind of notation before where we index the elements with a pair of numbers, so A11, A12 up to A1n, A21, A22 up to A2n, and down to AM1, AM2 over to AMN. Okay. So this is kind of a general expression for an M by N matrix. And then we say, or we'll agree, that, that if we want to focus on the ijth entry, so we could do that by taking the matrix, its name, putting in the square brackets and putting a little subscript ij, that means the entry in the ith row and jth column, okay, which in this case would be little a ij. Okay. All right, so then in terms of that notation, then we could rewrite the operations that if A and B are both M by N matrices, then the sum A plus B is described by the following rule, that the ijth entry of the sum is the ijth entry of A plus the ijth entry, of B. Okay. Similarly, the difference A minus B, the ijth entry of A minus B, is the ijth entry of A minus the ijth entry of B. And if we wanted to just do a scalar multiplication, if we take lambda times A, then the ijth entry of that is just lambda times the ijth entry of A. So those equations describe the operations at the level of entries. Okay, so then we have some properties of these operations. For example, if A, B, and C are all m by n matrices, then we have various laws such as A plus B equals B plus A. That's a commutative rule for addition. We have that A plus B plus C, in that order, is the same as A plus B plus C. That's the associative law. Maybe I'll write down the name. So the first one is the commutative law, and the second one is the associative law. And there's also distributive laws with respect to scalar multiplication. So for example, if you have lambda times mu times A, so lambda and mu are two numbers, then that's the same as lambda mu times A. That's a kind of a distributive law. And another kind of distributive law is that if you have lambda times A plus B, that's the same as lambda times A plus lambda times B. So that's a second kind of distributive law. Okay, so this is all well and good, and this actually makes the space of m by n matrices into what we sometimes call a linear space. So then sometimes we introduce this kind of notation, then capital M, Mn, is the space of all m by n matrices. And then this is what we sometimes call a linear space. It's a lot like the vector space of Rn that we've been talking about in the context of vectors, except now the objects are matrices. But you still do the same kinds of thing. You can perform linear combinations. Okay, so you can form linear combinations of matrices in this space. There's a special element in this space which is worth mentioning. Okay, the matrix in Mn with all components or entries 0 is, well, often we just write a sort of a bigger 0. So it's the matrix with all zeros everywhere. Okay, there's m rows and there's n columns. Okay, so that's all kind of well and good, but what really makes matrix arithmetic so interesting is that there's also a matrix multiplication. And the matrix multiplication is not component-wise, okay? And it's the matrix multiplication that really imbues the subject with its richness. So let's talk about matrix multiplication. And again, to be honest, this story is made a lot more intelligible, really, and a lot more general and natural if you go to Maxwell theory, where things simplify to quite an extent. But anyway, here's the classical story. So the classical story is that you can multiply matrices if their sizes are related in a very particular way. So if A is an M by N matrix, say, and B is a N by, say, P matrix, then the product A times B is defined. It is defined. So we do not multiply any old pair of matrices. They have to be specially oriented so that the number of columns of A equals the number of rows of B. That's the kind of critical condition contained in the fact that this n here and this n here are the same. Okay, so this n here is telling you the number of columns in A, while this n here is telling you the number of rows in B, and we're assuming that those are equal. And the way I want you to visualize this is like this. So here's a matrix A, and I'm going to just draw it like this. So here is, like, that is the number of rows, let's say M, and here is the number of columns, that's, say, N. So here's our matrix A. And then we have a matrix B that we're going to multiply it by, but the B is going to be on the right-hand side. So the crucial condition is that the size of B in this direction, the number of rows of B, is the same as the number of columns of A. Here's matrix B. And the number of columns of B, well, that's some P. All right? So here we have an M by N matrix, M rows, N columns. And here we have an N by P matrix, N rows and P columns. And as before, this number and this number agree. Okay, and geometrically that means that this width here is the same as this height. So that's sort of at the level of what they actually look like on the page. Okay, so if that condition is satisfied, then you can take the product. And what's their product going to look like? The product is going to look like, well, it's going to be something about like this and like this. So here's the product AB, and its size in this direction is M, and its size in this direction is P. Okay. So the result of an M by N times an N by P is an M by P. All right. So notice that we're taking the two unused dimensions here, the M and the P, and they are just being copied over here, M and P. Okay, so that's when you can multiply matrices, and that's sort of what it looks like. But what actually is the definition of the product of matrices? So the way I want you to think about this is the following. The simplest case is when we have a row vector times a column vector. Okay, so let's say A1, A2 up to AN. So that's going to be a matrix with one row and n columns. And we're going to multiply it by another vector, B1, B2 to Bn, which is something with n rows and one column. Okay, so this is allowed because that n and that n are the same. And the result of this is, as we've seen before, it's just essentially like a dot product. Dot product of this row vector with this column vector. So it's A1 times B1 plus A2 times B2. So the sum of all such products all the way down to AN, BN. Okay, and that's a 1 by 1 matrix. Now, sometimes people don't actually, put the 1 by 1 matrix in brackets, but probably officially we should, because we're agreeing that matrices are going to be put in brackets. So even a 1 by 1 matrix still deserves to be in brackets. Okay. So this is the simplest case, and once you've understood this one, well, then the general story is kind of just repeating this as many times as you can. So now let's look at the general case. Okay, I'll try to use the same dimensions as I had up here. Okay, so here's our first matrix. It's the matrix A, okay? And it's an M by N. And then over here is the matrix we're calling B. Maybe I'll make it like this, B. And it's an N by P matrix. Okay. And over here, what we should get is another matrix called A times B, which should be an M by P matrix. So something like that. So what are we doing here? So what we're going to be doing is looking at the matrix A and looking at the rows of A. So A has altogether M rows. Okay, so there's the rows of the matrix A. And on the other side, B has columns. And the condition on A and B guarantees that the rows in A have length n, and the columns in B have length n. Okay, so this dimension here is the same as this dimension here. And that means that we can multiply any one of the rows in A with any one of the columns in B. So for the general case, what we do is we multiply all possible rows of A with all possible columns of B. So how many possibilities are there? Well, there's M rows of A, and there's P columns of B. So altogether there are M times P different possible products between the rows of A and the columns of B. And what we're doing when we write down A times B is we're just organizing those various products in a systematic way. There's M times P different entries in A, B, and each one of those entries is obtained by taking a product of a row in A and a column in B. And I'm going to denote that like this. So here is the ijth entry, okay, of the product AB. And what is in here is the product of the product of ith row of A and the jth row of B. Okay? So that means this is sort of like the ith thing here, and this is the jth thing here. That means we have to go over to the ith position here in the matrix A and pick out that ith row. There it is right there. Okay, and then we have to go over to the matrix B and pick out the jth column. Okay, maybe it's right there. There's the jth column of B. And we're going to multiply this ith row of A with the jth column of B. And we're going to put the result of that, which is a 1 by 1 matrix, or just a single number, we're going to put it right in here. Okay, and we're going to do that for all possible rows of A and all possible columns of B. Okay, well, let's illustrate this with some examples. So suppose that we have, say, 1, 2, 3, go back to this, 1, 2, 3, 4, 5, 6, and I'm going to multiply it by some other matrix. I'm going to multiply it by a 3 by 3 matrix. This happens to be a 2 by 3 matrix. I'm going to multiply it by, actually, I might multiply it by a 3 by 4 matrix, okay, to give us lots of practice. Okay, so what's the 3 by 4 matrix? Maybe 1, 0, minus 1, 4, okay, that's 3 by 4, 2, 1, minus 1, 2, 4, 2, 0, 5. Okay, so there is a 2 by 3 matrix on the left, a 3 by 4 matrix on the right. We can check that this dimension and this dimension agree. So these two matrices do have a legitimate, well-defined product. But this dimension here equals this dimension here. So we are okay. We can make this product. All right, so now what we have to do is we have to take all possible products between these two rows here, two rows there, and there are 4 columns here. Now, the way I would suggest you to do this is the following. So we know what the final picture is going to be. It's going to be a 2 by 4. So 2 in this direction and 4 across. So we're going to get a 2 by 4 as a result of it. And to compute this, what I suggest you do is that you start with the first column. Compute the first column here. Okay, so there's going to be 2 entries that we're going to compute. And what that amounts to is by starting with this column here, this first column of B, and multiplying it by each of the rows of A. The results of those 2 products will end up in this column in the product. Let's do that. All right, so this first entry here, which I'm going to compute, this is going to be maybe it's a number which is 1 times 1 plus 2 times 2 plus 3 times 4. Okay, which is 1 plus 4 plus 12. 1 plus 4 is 5, plus 12 is 17. So there's 17 that goes right there. The next entry, this one down here, okay, that's going to be, maybe I'll come down here. It's going to be the product of the vector 4, 5, 6 with 1, 2, 4. So it's 4 times 1 plus 5 times 2 plus 6 times 4, which is 4 plus 10, that's 14, plus 24. 14 plus 24 is 38. So I've done the first column of the product. Now I'm going to go to the second column. Okay, so the second column over here, to compute that second column, I'm going to go to the second column in the matrix on the right-hand side and multiply it by each one of the rows of the left-hand matrix A. Okay, so what's that? I'll just write down the answer. So it's the vector 1, 2, 3 times the vector 0, 1, 2. So we get 1 times 0 plus 2 times 1 plus 3 times 2. And it's best if we do this in our heads, so you get to practice some arithmetic. Okay, so 1 times 0 is 0. 0 plus 2 plus 6 is 8. And then the next entry, we look at the second row of A, the 4, 5, 6 vector, and still multiplied by that same column 0, 1, 2. So 4 times 0 is 0. 5 times 1 is 5. 6 times 2 is 12. 5 plus 12 is 17. So there's a 17 here. Now we work on the third column. That means we have to now take the third column over here and multiply it by all of the rows of A. So 1 times minus 1 is minus 1. 2 times minus 1 is minus 2. 3 times 0 is 0. So minus 1, minus 2 for a total of minus 3. And then the next one, 4 times minus 1 is minus 4. 5 times minus 1, that's minus 5. 6 times 0, so it's a total of minus 9. And then finally, our fourth column over here is obtained by going to this fourth column over here and multiplying it by the 2 vectors. So 1, 2, 3 times 4, 2, 5. 4 plus 15. That's 8 plus 15, that's 23. And the next one, 4, 5, 6 times 4, 2, 5. So that's 16 plus 10, that's 26, plus 30. 26 plus 30, 56, I think. Okay? So this is how I want you to think about things, okay? When we multiplying matrices, you're multiplying the rows of the left one with the columns of the right one. Okay? And you're going to get a number for each possible product. That's what you do. And so you're just organizing all the possible products. Now you might think, well, this is a kind of a crazy thing to do. It's rather complicated, but it's not that bad. But we'll see that this is really a remarkable operation. Okay, and there's a main reason why this is remarkable. This remarkable operation satisfies a somewhat non-obvious but key property. We're going to say this is a theorem. Okay? The theorem is that matrix multiplication is associative. That means, okay, what does that mean? That if, say, A is an M by N, B is N by P, and C is, say, P by Q, then we're allowed to multiply A, B, because this N and this N are equal. And then we'll get an M by P matrix, which we are allowed to multiply by C. So this product makes sense. A, B times C makes sense. On the other hand, B times C also makes sense, because if we go to B and C, this P and this Q are the same. So that means this product here, BC, is defined. And the result of that will be an N by Q. And we can multiply that by A, because the last index is N in A. So both the left and right hand side are well defined. And the absolutely remarkable and beautiful fact is that this thing is associative, that AB times C equals A times BC. Okay, this is a great, and at this level it should be surprising, because, you know, why should this be true? Actually, what's one of the advantages of the Maxwell point of view? If you look at the Maxwell sort of orientation, you see that this is sort of true for much more obvious reasons, but okay. Now there's a few more things. We're going to go back to this theorem, so we have to understand this theorem. But I just want to mention a few things. So a key point is that matrix multiplication is not commutative. Okay, so I'm going to illustrate that with an example. So let's have a look at, I'll stick with the 2 by 2, because then the situation's not so onerous to do by hand. So suppose we have the matrix 1, 3, 4, minus 1, and that's usually how I'll read things. I'll read on the first row and then the second row, 1, 3, 4, minus 1. And here's another matrix, let's say 2, 1, 1, maybe minus 1, 5. Okay? So this is 2 by 2, this is 2 by 2. Let's see what the product is. The product is going to be defined because this 2 and this 2 agree. So what is that product? So remember what I told you. You start with the first column here and you multiply it by each of the rows over here. The first entry will be 2 times 1 plus 3 times minus 1. That's minus 1. And the next entry below it will be 4 times 2 plus minus 1 times minus 1. That's 9. And then for the next column, we go to the second column over here and still multiply it by the 2 rows over here. So the first entry will be 1 times 1 plus 3 times 5, which is 16. And the next entry is 4 times 1 plus minus 1 times 5. So it's 4 minus 5, that's minus 1. Okay. But let's look at the same 2 matrices but multiplied in the different order. So 2, 1, minus 1, 5 times 1, 3, 4, minus 1. Let's do that product. Okay, so just to be consistent, so we're going to start with this column here. You don't have to do this underlining or circling. I'm just doing this so you can see what's happening. But shortly, we're not going to be doing this anymore, okay? But just to start with, it's good practice. Okay, so let's multiply these 2 rows by this first column, 1, 4. So what do we get? 2, 1 times 1, 4 is 2 plus 4, that's 6. And then below it, minus 1 plus 20 is 19. And now the second column we get by multiplying the 2 rows here by the second column, 3 minus 1. And that gives us 6 minus 1, which is 5, and minus 3 minus 5, which is minus 8. Okay, so this is an example that A times B does not equal B times A in general. This is very important. Okay? This is distinguishing this new arithmetic from the familiar arithmetic that we're used to with ordinary numbers. With ordinary numbers, multiplication is commutative. 3 times 5 is the same as 5 times 3. But here with matrices, crucially, it's not. But the associativity of multiplication, that is satisfied. So in our next lecture, we'll start by looking more carefully at this matrix multiplication and seeing that it really is associative.